Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Okay, so imagine this. The entire tech industry is screaming about a global memory shortage. AI models are so hungry for RAM, they're literally stealing it from the smartphones in your pocket, making new phones worse. Billions are being poured into new factories. Everyone thinks hardware is the bottleneck.
And then, out of nowhere, Google drops a paper. Not a new chip, not some crazy manufacturing breakthrough, just math. And suddenly, Wall Street loses its mind, wiping billions off memory chip giants because they think the problem is solved.
But here's the kicker. Wall Street totally got it wrong. Not only is the problem not solved in the way they think, but this mathematical breakthrough is actually going to make the demand for memory explode even further. It's a classic counterintuitive tech curveball.
It's less problem solved and more problem shifted, magnified, and now coming to a device near you. It's wild.
Wild is an understatement. For the past 2 years, it felt like we were living in a constant state of AI-induced hardware anxiety. Every new LLM that dropped, every incredible demo, came with this silent asterisk. If you can afford the HBM, high bandwidth memory, right? That specialized RAM that AI servers just devour?
Exactly. And it wasn't just a quiet background hum. This was a full-blown crisis. If you track the supply chain for memory manufacturers like SK Hynix or Samsung, they were literally pivoting entire fabrication plants to crank out HBM for these AI data centers, which meant less traditional DRAM for everything else.
And everything else meant our laptops, our PCs, and crucially, our smartphones. It wasn't some abstract problem for cloud giants, it hit home. I remember Qualcomm's earnings call in early 2026. Their CEO, Cristiano Amon, basically stood up and said, "Hey, we're making a ton of money, but AI data centers are eating our lunch. Memory shortages are going to define the scale of the handset industry."
That was the tipping point. He was saying, point blank, that AI was actively starving the smartphone supply chain. The laws of supply and demand kicked in, DRAM prices went through the roof, and suddenly, major smartphone manufacturers, especially the ones in China, couldn't even get enough memory chips to build the phones they wanted to.
So my fancy new phone couldn't get built because a data center in Virginia needed more RAM for some chatbot. It's a digital game of Tetris where the AI arms race wasn't just Google versus Microsoft, but a battle between a supercomputer and the device in your pocket. And the supercomputer was winning.
And the consumer felt it. You could see it in the specs. Tech reporting from that period, like from Android headlines, was full of stories about quiet downgrades. Phones that were supposed to ship with 12 or 16 gigs of RAM were suddenly coming out with 8. You started seeing plastic frames again instead of aluminum or titanium. Even display quality took a hit, reverting to 90 Hz screens when 120 Hz had become the standard.
So we were literally going backward in consumer tech because AI needed to run bigger models. And the consensus was the only way out was to build more factories, which takes years and billions of dollars. It felt like a physical, unassailable wall.
It did, and that's what makes what Google did so utterly shocking. They didn't build a new factory. They didn't invent a new chip architecture. They just wrote some code.
A piece of code that effectively said, hey, all that memory you thought you needed, you actually need 6x less. It's like finding a cheat code for reality. But before we get into the how, we have to understand what they were targeting. This isn't just any old memory. It's specific to the AI's short-term brain, right? The KV cache?
Exactly, the key value cache. Think of it like the AI's digital cheat sheet or its working memory for a specific conversation. When you're chatting with a large language model, every single word it generates, or token, needs to remember the context of the conversation so far. It stores a mathematical representation of that word, a key and a value, in this KV cache.
And that's so it doesn't have to reread the entire chat history every time it generates a new word?
Precisely. It's about efficiency. But here's the problem. That KV cache grows linearly. The longer your conversation with the AI, the more memory it eats up. And these models are getting incredibly good at handling massive context windows. Thousands, tens of thousands, even a million tokens. Google research noted that running a 70 billion parameter model for just 512 concurrent users could burn through 512 gigabytes of cache memory alone. That's nearly 4 times what the model's actual brain, its weights, consumes.
So the problem isn't the model itself, but its short-term memory. That's where the bottleneck was?
A huge part of it. A 1 million token context window can easily push the KV cache into hundreds of gigabytes, far exceeding the 80 gigabyte limit of a single NVIDIA H100 GPU. It's the equivalent of trying to hold a novel's worth of information in your head for every single sentence you speak.
Enter TurboQuant. This is where Google steps in. On March 24th, 2026, they published this paper that basically redefines what's possible.
A bombshell, truly. The paper, TurboQuant, Online Vector Quantization with Near Optimal Distortion Rate, came from Google scientists Amir Zandier and Vahab Mirrokni, along with collaborators. Their claim was staggering. They could compress the KV cache from its standard 16-bit float format down to just 3 or 4 bits. That's a 6x reduction in memory footprint. For the same amount of physical memory, you could have 6 times the context or 6 times the users.
6 times? And with 0 accuracy loss? That's the part that always makes my skepticism meter redline. In the tech world, compression usually means degradation, right? Like a super compressed JPEG image gets pixelated. When you quantize AI models, they tend to get blurry. They hallucinate more. They lose reasoning.
Absolutely. My first thought was, okay, so what did you break? Because typically, if you shrink an AI model this much, you're sacrificing something significant. You're losing nuance, losing its ability to reason. But the Google researchers were adamant: 0 accuracy loss and no need for fine-tuning or retraining the model. This wasn't a hack. It was a fundamental algorithmic improvement.
And they put their money where their mouth was. They didn't just test it on their own proprietary models. The paper highlighted tests on open-source heavyweights like Meta's Llama 3 8B, Mistral 7B, and even their own Gemma 7B.
They ran it through grueling long-context evaluations, including the infamous needle-in-a-haystack test, which forces an AI to find a tiny piece of specific information buried in a massive document. And across benchmarks like Longbench and Zero Scrolls, TurboQuant maintained absolute quality neutrality at 3.5 bits. Even at 2.5 bits, the degradation was marginal.
So it wasn't just good enough, it was essentially indistinguishable from the uncompressed version. But here's the kicker. It wasn't just about saving memory. The paper also showed that because the memory footprint was so much smaller, data moved faster. TurboQuant actually achieved up to an 8x performance increase in computing attention scores on NVIDIA H100 GPUs compared to unquantized models. It's not just smaller, it's faster.
That's the part that really blows my mind. You're effectively getting more from the same hardware, not just by being efficient, but by making it faster, too. It's like your car suddenly gets 600 miles to the gallon and goes from 0 to 60 in 1 second.
Okay, so this is where we have to try to unpack the math magic without needing a PhD in computer science. How did they achieve this? Because traditional quantization, as you said, struggles with messy data. If you try to shrink all the numbers in a high-dimensional vector with a uniform grid, you introduce massive rounding errors.
That's the core problem. Imagine you have this incredibly complex, spiky sculpture, and you're trying to shove it into a small square box. If you just try to uniformly compress it, you're going to break off all the spikes, right? That's what happens with traditional quantization. The AI's internal mathematical representations, these vectors, are not uniformly distributed. Some numbers are huge, some are tiny. If you try to shrink them all the same way, you lose critical information, and the AI hallucinates.
So TurboQuant's first stage, PolarQuant, is like reshaping the sculpture?
Precisely. Before they even try to compress, they apply what they call a random orthogonal rotation to the data vectors. Think of it this way. Instead of just squishing the spiky sculpture, PolarQuant rotates and reshapes it until its mass is perfectly, uniformly distributed into a smooth sphere. It's still the same sculpture, but now it's perfectly round.
So by mathematically rotating the data, they spread out all that energy or information uniformly across all its coordinates. And once it's smoothed out into a predictable bell curve-like statistical distribution, then it's easy to apply standard compression without losing the core meaning.
Exactly. It's brilliant. That first stage, PolarQuant, uses about 2 to 3 bits of data to achieve this. It makes the data quantization friendly without losing fidelity.
But even with that elegant rotation, there's always a tiny bit of mathematical error, right? Left unchecked, those tiny rounding errors compound, especially in a long conversation, leading back to those dreaded AI hallucinations.
Yep, and this is where the second stage, the quantized Johnson-Lindenstrass transform, comes in. This is their one-bit safety net. To fix those tiny leftover errors from stage 1, they take that error, project it through a random mathematical matrix, a geometry formula from 1984, by the way, and store only the sign bit, just a literal +1 or -1.
A single bit to correct everything? That's insane.
It acts as a mathematical bias corrector. So when the AI goes to retrieve a memory from its cache, that one-bit safety net perfectly corrects the trajectory of the math, ensuring the final attention score is unbiased and accurate. It's like a tiny, perfectly calibrated rudder on the massive ship.
This is where I start wondering if code is officially outpacing silicon. For years, the narrative was that Jensen Huang and NVIDIA held the keys to the future because they controlled the physical hardware. Whoever had the most powerful GPUs won. But TurboQuant basically says, hold my beer. A handful of mathematicians at Google can effectively create 500 gigabytes of GPU memory out of thin air just by writing a better equation. Is this a fundamental paradigm shift? Are we overvaluing hardware companies and undervaluing algorithmic research?
It certainly feels like it. The immediate dramatic leaps in AI capability right now seem to be coming from these mathematical optimizations. Don't get me wrong, hardware still matters, but for the first time in a while, software just leapfrogged a massive hardware constraint. It's a testament to the power of pure theoretical computer science.
And Wall Street, bless their cotton socks, immediately misinterpreted this. The minute this paper dropped, the financial markets reacted with immediate, unnuanced panic.
Oh, it was glorious. If an algorithm can instantly make AI models require 80% less memory their logic dictated, then the insatiable demand for physical memory chips must be over.
And the outcome?
Within 24 hours of the announcement, shares of memory chip giants like Samsung Electronics and SK Hynix, the primary manufacturers of HBM for NVIDIA GPUs, plummeted by 5% to 6%. The narrative was simple. Software had solved the RAM crisis, and the semiconductor supercycle was dead.
That's what you call a dumb money moment. Because it didn't just hit the HBM manufacturers, did it? The panic spilled over into companies that manufacture entirely unrelated hardware.
Exactly. Investors reportedly started dumping stock in companies like Seagate and SanDisk, which is Western Digital. These companies primarily make NAND flash memory and hard disk drives, which are used for long-term storage, where your photos and files live when the computer is off.
So your vacation pictures, not the AI's short-term brain.
Precisely. TurboQuant specifically targets the volatile GPU working memory, the HBM, DRAM, SRAM, used during active AI computation. Compressing the KV cache has absolutely zero impact on the global demand for long-term NAND storage. It highlights the massive disconnect between the engineers building the future and the financiers trading it. They saw AI, memory, and compression in a headline and just hit the sell button indiscriminately.
So if Wall Street got it so spectacularly wrong, what's the actual counterintuitive aha moment here? If AI memory is 6x cheaper, it doesn't mean we use 6x less of it, does it?
Not at all. And this is where we bring in the Jevons paradox. It's a principle from 1865, coined by Victorian economist William Stanley Jevons. He observed that when James Watt invented a much more efficient steam engine, coal consumption didn't go down, it tripled.
Because it became so much cheaper and more efficient per unit of work that it became economically viable to put a steam engine in every factory and every ship. Suddenly, everyone wanted one.
Exactly. The parallel here. Earlier in 2026, Microsoft CEO Satya Nadella actually cited the Jevons paradox to explain AI infrastructure. He said, "As AI gets more efficient and accessible, we will see its use skyrocket, turning it into a commodity we just can't get enough of."
So if TurboQuant reduces the memory cost of running an AI model by 6x, Google and Meta aren't going to buy 6x fewer GPUs. They're going to train models that are 6x larger or process context windows that are 6x longer, keeping their hardware utilization exactly at 100%. The demand doesn't drop, it just shifts to more ambitious uses.
Which means the memory market isn't destroyed, it explodes. But here's the real disruption, the part that's going to hit consumers, the edge AI future.
Meaning AI moves out of the cloud and onto our devices?
Exactly. If you can shrink the KV cache by 6x, you no longer need a massive data center to run a highly capable long-context AI. You can run it locally, on battery-powered hardware. Just days after the TurboQuant news, a startup called Prism ML emerged from stealth. They released Bonsai 8B. Using extreme quantization techniques, conceptually similar to Google's breakthroughs, they packed an 8.2 billion parameter model into just 1.15 gigabytes of memory.
1.15 gigs for an 8 billion parameter model? That's tiny.
And the result? They successfully ran a frontier-level AI model locally on an iPhone 17 Pro Max at a blistering 44 tokens per second using a fraction of the battery power.
So the ultimate conclusion here is that Wall Street panicked because they thought TurboQuant would kill the memory market. But the reality is the exact opposite. By making it possible to run massive 32,000 token context windows locally on a smartphone without needing the cloud, TurboQuant is going to drive an unprecedented upgrade cycle.
Consumers are suddenly going to demand smartphones, laptops, and smartwatches with faster, highly optimized local memory to run their personal AI agents. The RAM crisis isn't over. The battleground has simply shifted from the server farm to the pocket. We're going to need more memory than ever, just configured differently.
So what are the big takeaways from all this? First, it really highlights how we might be overvaluing hardware companies and undervaluing algorithmic research. This was pure math, not new silicon, that caused this seismic shift.
Absolutely. And related to that, the velocity of open source is incredible. Within 24 hours of Google's paper dropping, the open source community was already submitting pull requests to integrate TurboQuant into major AI libraries. This isn't locked behind a Google API. It's a mathematical concept that the entire ecosystem is weaponizing immediately.
And for those of us who suffered through the smartphone downgrades, does this mean the smartphone supply chain will recover? Will Qualcomm's customers be able to stop gutting phones now that the software is doing the heavy lifting?
That's the big question. It should alleviate some pressure, but the Jevons paradox, or the rebound effect as some call it, is a sneaky one. As Wei Wang, a computer architect at ByteDance, noted, efficiency gains are necessary but not sufficient for sustainability. The rebound effect can exceed 100%. If we make AI 6x cheaper to run, we might end up using 10x more of it, potentially straining the power grid and memory supply chains even further down the line. It's a continuous cycle of demand.
The next time your phone stutters because the manufacturer cheaped out on RAM to pay for a data center, just remember, some mathematician at Google is currently trying to fix your hardware problem using nothing but a whiteboard and a geometry formula from 1984.
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.